With that, ladies and gentlemen, Dr. Pearce will also be taking his leave from the conference. We thank him with a round of applause, shall we, ladies and gentlemen? Now, as our dignitaries make their way to their seats, we will now move on to the conference, ladies and gentlemen. This, of course, will be our first keynote speech. Dr. Pearce is the director of the SKA Low Telescope, soon to be built in Western Australia, as part of a $2 billion project, ladies and gentlemen, International SKA Observatory. She has also worked at Australia's National Science Agency, CSIRO, for 10 years in the fields of space and astronomy, and spent 6 months in early part of 2021 as CSIRO's acting chief scientist. With that, ladies and gentlemen, it's given me enough time to clear the stage. The boys have done very well, haven't they? Yep. Please join me in welcoming right now, ladies and gentlemen, Dr. Sarah Pearce, who will be delivering her keynote speech on the SK Observatory, meeting the data challenge for next generation of radio astronomy. Dr. Sarah Pearce.
Good morning, distinguished guests, other speakers and attendees at the conference. Thank you very much for inviting me to speak today. I'm sorry that I couldn't be there with you in person. Our borders in Western Australia are still closed, but I'm very pleased to be able to join you digitally. To begin, I'd like to acknowledge the Whadjuk Noongar people as the traditional custodians of the land and waters that I'm speaking from today in Perth, Western Australia. And I pay my respects to their elders, past and present. I also acknowledge the Wurundjeri Yamaji as the traditional owners of the Murchison Radio Astronomy Observatory, on which the SKA in Australia will be built. And of course, I'd like to welcome and acknowledge any traditional owners or First Nations people who are here in attendance today. It's my pleasure to be able to join you to talk about a revolution in astronomy that is pushing the frontiers of supercomputing and engineering. And I'm talking, of course, about the SKA, the Square Kilometre Array. The SKA is a next generation radio astronomy facility that will revolutionize our understanding of the universe and the laws of physics. But it is also an exascale science and computing project that will push forward the boundaries of scientific endeavor, computational innovation, and engineering capability for many decades to come. And your innovations in the supercomputing sector are part of the fabric that will make this ambitious goal possible. Could we start the video, please?
Gravitational waves. How does magnetism work throughout the universe?
Come si formano I pianeti?
How many gravitational waves are passing through me right now?
What is dark matter?
What is the impact of magnetic fields on the formation of galaxies?
宇宙の歴史はどうだったか?
¿Estaba Einstein en lo correcto?
And for me, the most important, is there life out there?
We ask ourselves, what is the most useful thing that a radio telescope can contribute to the answer to these big questions? We are building a time machine. We're looking at what our surroundings were like almost at their inception. The question is, how are we actually going to make this happen?
So that's an inspiring introduction to the SKA Observatory, which is the global collaboration in charge of building the SKA project, which will consist of 2 of the most advanced radio telescopes on Earth. So we'll take a look at how radio astronomy via the SKA will let us map the sky and make discoveries about the universe that no other telescope is capable of. Now, I don't think my clicker is moving the slides on as it is meant to, so I'm going to ask if the people could please move the slides on to the next one after the video. Thanks. So the first pioneers of astronomy used only one aspect of light, optical light, to make their discoveries. You can see it here. It's a relatively small band in the middle, but it's only one part of the vast electromagnetic spectrum. We now have powerful instruments that can study light across this whole spectrum. And with these instruments, we have begun to unravel the mysteries of our universe piece by piece. Far to the left on this diagram is where we play, in the radio regime. Here, each photon, the fundamental particle of light, has 1 million times less energy than in optical light. And radio astronomy is a relatively recent branch of astronomy. But since the first radio antenna was pointed at the sky in 1931, you can see that there has been an explosion in the construction of radio telescopes. To start to get an appreciation of the level of detail and information that we can gather from radio astronomy, let's look into the heart of our own Milky Way galaxy. Next slide. Here it is in optical light. This is what you'll see if you look in the sky yourself. But here it is in radio waves. This is the view of the Milky Way galaxy as gathered by the Murchison Wide Field Array telescope based here in Western Australia. And this is a close-up of the galactic center made by Meerkat, a radio telescope which is an SKA precursor in South Africa. So with radio telescopes, we can observe the invisible universe. Radio light is not hindered by the gas or the dust in space or by our atmosphere. So radio telescopes are one of the best ways to spot black holes in galaxies or the effects of black holes on their immediate surroundings. In fact, radio telescopes made the first close-up image of a black hole in 2019. They're also good at detecting pulsars, very fast spinning cores of exploded stars. And they give us a unique view of the cosmic microwave background, which is the remnant energy left over from the Big Bang. So radio astronomy is how we can look into the furthest reaches of space, not just across large distances, but back in time. So in that way, we are building a time machine, looking as far back, as close to the birth of the universe, to solve some of the biggest and most complex mysteries facing humanity. So what will we be looking for with the SKA telescopes particularly? Our science goals are broad and ambitious. Looking back into the history of the universe as far as the cosmic dawn, when the very first stars and galaxies formed, we're aiming to answer some of the biggest questions of astrophysics. How and when did those first stars and galaxies and black holes form? What are the mysterious properties of dark energy? And what is its role in the universe? Where did galaxies come from and where did they go? How did the universe become magnetic? Was Einstein right about gravity? And we'll try and test this by measuring fast spinning pulsars. Where do gravitational waves come from? And of course, the eternal question, are we alone in the universe? And on that final point, the SKA telescopes will be uniquely suited to address the search for extraterrestrial intelligence, or SETI. For the first time, we'll be able to detect emissions from planets around nearby stars if they were giving off the same kind of signals that we generate from human activity on Earth. The SKA has been a long time in the preparation. It's 25 years since we first dreamt of this next generation radio telescope. We now have a global collaboration of 16 countries, bringing together more than 1,000 engineers and scientists from 270 different institutions. And to make this dream a reality, later this year, we will start to construct 2 complementary arrays of radio telescopes, one in Australia and one in South Africa. Our telescopes will be built, operated and maintained by the SKA Observatory, who I work for, an intergovernmental treaty organization like the UN or the European Space Agency. This is only the second time that world governments have set up this kind of treaty organization for astronomy. We're bringing together nations from 5 continents under a single entity. The SKA telescopes will monitor the sky in unrivaled detail and map it tens of times faster than any current radio facility. Their antennas will be built hundreds of kilometers away from large population centers in areas that are radio quiet. So they don't have many people, and so they don't have artificially generated interference from our phones and our computers and our cars, which would swamp the faint radio signals that we're trying to detect. So we are building one global observatory with 2 telescopes across 3 sites. SKA Low in Australia is the low frequency array that will soon start construction in the remote Murchison region in Western Australia. It will have 512 clusters like this one that you can see here, each of which has 256 antennas. That means a total of 130,000 2-meter tall antennas spread out in spiral arms across the desert for more than 65 kilometers. And these are low frequency antennas, so they cover the range 50 to 350 megahertz. Our other telescope is SKA Mid, the mid-frequency array of dishes that will be built in South Africa. Here we will have close to 200 dishes, most of which will be 15 meters in diameter, spread across more than 150 kilometers of the Karoo. And these, as the name suggests, will be higher frequency than SKA Low. They'll operate between 350 megahertz and 14 gigahertz. And I said there were 3 sites, only 2 telescopes, but 3 sites. And here is our 3rd site, our headquarters, the Global SKA Observatory headquarters at Jodrell Bank in Manchester in the UK. It's from here that development, construction, and operations of the telescopes will be coordinated across the 2 host country sites. And our headquarters sits in the shadow of the historic Jodrell Bank Observatory, which is a UNESCO World Heritage Site. But in the lead up to SKA, many groundbreaking radio astronomy facilities are helping us to prepare. The knowledge gained by these precursors and pathfinders is guiding the SK Observatory through construction and operation. We will be building on the experience of all these telescopes to be at the heart of the groundbreaking science that we're going to deliver for many years to come. So that's all very well, but why am I here at a supercomputing conference talking to you? Well, you may hear the SKA referred to as a software telescope. Many of the critical features that will make this next generation telescope a success are only going to be possible through software and computing. Due to the sheer volume of information that we have to transport, process, store, and distribute to end users around the world, we consider the SKA project to be the ultimate big data challenge. So I'm going to take you briefly through the data journey from light to byte. That is from the source in space that we're observing all the way to the final user who will be analyzing the data. And our journey begins when radio waves emitted by objects in the universe reach our telescopes. They're captured by the antennas or they bounce off the dishes and land on the receivers. The radio waves induce voltages in the antennas and receivers, and then we digitize these voltages using software-enabled circuitry. And then optical fibers transport this newly digitized data from the telescopes to the central processing facilities, or CPFs. And here we combine the signals using FPGAs and GPUs, and even some CPU, GPU, FPGA hybrids. And then that's where it gets even more complicated. The SKA will be able to distinguish 65,000 different radio frequencies simultaneously. So 65,000 colors of radio light sampled through 130,000 antennas. This is big data. Once the signals have been separated in frequency, there are 2 ways we can process them, depending on what we're looking for. We can stack signals together for what we call time domain data. This lets us detect repeating objects like pulsars or bright one-off events like gamma ray explosions and fast radio bursts. But we can also use these radio signals to make images of the sky, what we call image domain data. To do this, we take the signals from each pair of antennas as a baseline, and we multiply them together, essentially, developing data objects we call visibilities. Of course, we have to do this for 200 dishes, 512 groups of 256 antennas. That's 150,000 baselines in 65,000 different frequencies, up to 10 billion data streams. Once the signals have been processed in the CPFs, they move to our science data processors. So 2 supercomputers, one in Cape Town for our dishes and one in Perth at the Pearce Centre for our antennas. And the science data processors are an absolutely integral part of the SKA telescopes. They must be able to keep up with the data pouring in from the receivers 24/7. Using the time domain data, we will search more than 1.5 million candidate objects every 10 minutes for rare phenomena like pulsars. But the most difficult computing burden is making sense of the incoming 10 billion visibility data streams. Because the visibilities include both the image of the sky that we want, but also the response of the antenna and the response of the atmosphere that's in front of the image. The supercomputers will use complex Fourier transforms and machine learning to decipher these signals, removing the signals coming from the antennas and the atmosphere and any radio interference. This is high performance data analytics, but without it, our observations would be indecipherable. Then once the data leaves the science data processors in South Africa and Australia, they'll be distributed on dedicated fiber to SKA regional centers spread around the globe. The science data that emerges from the telescopes needs to be reprocessed and analyzed by scientists, but of course the data volumes are far too large to deliver them straight to the end users. Scientists won't be able to download their data products, let alone process them on their home computers or even their university network, because these are not bite-sized products, they are petabyte-sized. So we have this network of centers that will be developed around the globe, providing end-to-end support for the users and the science data products and the archives. And they will act as the windows to the observatory for the scientists, enabling the world-leading science SKA promises. And the scientists will need to use the computing power of these regional centers pooled together in order to analyze their data products. Of course, signal transport and networks will be the backbone of the SKA Observatory. They will interface with almost every aspect of the system and represent the largest and probably most challenging network in science. From the dishes, for example, we will have an average of 8 terabits a second being transmitted, 100,000 times faster than the projected average broadband speed in 2022. And the physical network will use optical fiber to carry huge amounts of data over long distances at high speed. We'll need around 100,000 kilometers of dedicated optical fiber, enough to wrap around the Earth twice. This will give our astronomers using the SKA access to more data than has ever been available in the history of radio astronomy. And to process this enormous amount of data, we'll have the two science data processors will each need to have a processing speed of approximately 125 petaflops a second, putting them in the top 3 of the fastest supercomputers at the moment. Overall, we'll have around 700 petabytes of data a year to add to the science archive across the regional center network. And the regional center network itself will have a collective computing capacity of around 500 petaflops a second. The processing and storage requirements of the telescope are so vast that the technology we need doesn't exist at the moment in a form we can afford. Fortunately, we have some time for the technology to catch up while we are constructing the telescope. In fact, we believe that SKA will energize and drive forward innovation to deliver our computing needs. So what will we get from this amazing processing power and information and these new telescopes? Well, radio telescopes are usually measured with two key performance indicators: resolution and sensitivity. Radio telescopes get better resolution by being spread further apart, and that acts a bit like a zoom lens in a camera. And sensitivity just depends on the total collecting area, how many radio photons we can gather. The SKA telescopes will outperform the existing state-of-the-art observatories in resolution and in sensitivity, and perhaps most clearly in survey speed, making our images sharper and more in focus, detecting much fainter details, but letting us survey greater areas of the sky more quickly. But of course, as well as achieving all this, we also need to consider our role as responsible global citizens. SKA has made a commitment to build and operate a sustainable observatory, minimizing negative environmental and other impacts. We've also made a commitment to play our part in addressing the UN's Sustainable Development Goals, including climate action and responsible consumption and production. Astronomy is a power-hungry science, like many sciences. A recent paper in Nature Astronomy calculated that astronomers in Australia are responsible for 40% more carbon emissions per year than the average person, and 60% of that footprint is a result of supercomputing. Similar estimates have been made in other countries, of course, and variations depend on the percentage of renewable energy, remoteness of the location, and other factors. But we calculate that electricity consumption by our telescopes and our computing facilities will be the largest source of our CO2 emissions, accounting for about 90% of the CO2 generated by the observatory. So this is where we're concentrating our greatest effort. Thanks to innovative design and adoption of more efficient technologies, we've halved the estimated power consumption for the SK telescopes, and we will aim to run as much power on site with renewables as possible. As an example, this is the current power station at CSIRO's Murchison Radio Astronomy Observatory, the MRO. This is where the SKA will be built. It's not the power station for the SKA, but it's likely to be similar. And the remote location of the MRO ensures that the environment is radio quiet, as we discussed earlier, but of course, access to basic infrastructure like roads and power is a challenge. The MRO uses a hybrid solar diesel power station, supported by one of Australia's largest off-grid lithium batteries. It is the world's first hybrid renewable facility to power a remote astronomical observatory. We will build on what CSIRO has learned with this power station when we come to commission our new power station for the SKA. The observatory is also working hard to reduce its supercomputing carbon emissions. So the two supercomputers have a current estimated consumption of 2 megawatts instead of the original estimate that we had of 6 megawatts. So they will be equivalent to the world's fastest supercomputers in 2019, but will use 3 times less power than the current industry standard, significantly lowering our carbon footprint. And these stringent requirements are driving innovation in lower power electronics that will benefit the SKA, of course, but also other technologies, contributing to lowering all our carbon footprint. And we are also in discussion with the regional centres around how we can realise a sustainable network so that together we can progress towards green computing at the exascale. In Perth, the Pearce Supercomputing Centre will host the SKA Low supercomputer. Pearce generate solar power from a rooftop photovoltaic system, but they also have a geothermal solution for cooling, which reduces electricity requirements. This innovative project was the first of its kind in Australia, and as of this year, it has saved 43.8 million litres of water. And we very much look forward to working with Pearce as we develop the supercomputer to put in for SKA, and that becomes a core part of the telescope. So how are we helping the member states and our users to prepare for and maximize the potential of these enormous amounts of data? Well, we have been running SKA data challenges, a series of challenges aimed not just at radio astronomers, but the broader astronomy, physics, and computing communities. Science data challenges invite the science community to solve a specific problem using simulated SKA data. Last year, we ran our second data challenge with 40 teams across 22 countries. They were tasked with using computer algorithms to find and analyze nearly 250,000 galaxies in a simulated data cube. The mock data set stacked radio images, each representing a different frequency, and was in total 1 terabyte in size, so too large for the teams to store and process on their own computers. And we were delighted that the Science Data Challenge received generous support from several major international computing facilities, letting teams access and process the huge data sets without needing to download it. This let us run the challenge in an accessible way and provided valuable tests as well for the future regional centers. These data challenges have highlighted key principles around collaboration, complementarity of methods, and reproducibility in line with our commitment to open science. We'll hold more of these challenges as we get closer to the start of science operations, because they're a real test bed for driving forward our new technologies, which will be relevant beyond SKA and potentially even beyond astronomy. If you're interested, please keep an eye out on the SKA Observatory website, and we very much welcome anybody who wants to participate. Just a few reminders of the SKA project in numbers while I move on to my final theme, which is the critical one for SKA, which I haven't mentioned until now. The SKA is a truly multicultural, multinational collaboration, and its diversity is a source of strength for our observatory. The technologies that are being built to contribute to the antennas will come from the world's best in different countries and will be integrated together in Australia and South Africa to build something that no one country would be able to do on its own. The SKA Treaty commits the organization to values of equality, diversity, and inclusion in its leadership and at all levels. And this covers things like gender balance, nationality, and traditionally underrepresented groups. So we will be a proactive voice in society to address global challenges and emergencies. We will inspire the next generation, and we will build strong relationships with local and Indigenous communities. Astronomical research as a whole continues to offer significant benefits beyond the astronomical discoveries. The boom in big data and high-performance computing for big science projects like the SKA will drive a revolution, fostering links with industry, creating jobs, and generating growth globally. So imagine you can come with me in 8 years' time when we have finished building the telescopes. And we can stand together in South Africa, in the Karoo, and in Western Australia, in the Murchison, surrounded by our vast arrays of antennas as they send terabits of data streaming through the desert to detect the faintest whispers from the dawn of the universe. Thank you for your time.